Now, in today's discussion, we're going to consider the other aspects or other pathways involved in the metabolism of carbohydrates, specifically the degradation of glycogen, the synthesis of glycogen, as well as the pentose phosphate pathway and the gluconeogenesis. We'll also consider the control, different ways in which we control um, or our organisms control the metabolism of carbohydrates. Alright, so in the previous discussion, we've learned the process of glycolysis, and we've learned um, the different steps in glycolysis and the control points in glycolysis. Today, we're going to expound more on what happens to some of the intermediates that have been implicated in glycolysis, or that are implicated in glycolysis, and also consider some other pathways, relative pathways, and more importantly, the way by which the organisms regulate the metabolism of carbohydrates. Alright, so first and foremost, we consider the substance called glycogen. Now, glycogen is actually very similar in structure to starch. We have discussed structure of starch in the past, and we've learned that starch is a branched molecule, right? Glycogen also is a branched molecule. In fact, the structure of glycogen is such that it's able to maximize the number of glucose residues that it can store, and that the organism can therefore utilize and expend in times of need. In fact, molecular modeling or mathematical modeling revealed that the structure of starch, or rather the structure of glycogen, which is by the way called animal starch, um, is such that it holds the maximum amount of glucose that, and therefore of energy for a glucose polymer that it can possibly store in times of need, and that the branching actually makes this possible. All right, so let us ask ourselves a very important question first. What happens, say for example, when you take in carbohydrate-rich meal? After the meal, you have a lot of glucose in your blood, right? So what happens exactly? So what happens is that during digestion, starting from your mouth, the salivary amylase, of course, digests the um, rice, for example, or bread or carbohydrates into its constituent maltose and glucose. Of course, these substances are these polymers and resulting disaccharides are ultimately digested even more in the small intestine. They cross the intestinal mucosa and then go into the blood. Now, the blood then becomes rich in glucose after a carbohydrate-rich meal. So you ask yourselves the question: what will the um, what will the body do with that um, flood of glucose molecules, or glucose carbohydrate or energy source? Well, we know that cells will never waste energy. It will only take in what it needs, and take it will not metabolize what it does not need, right? So if there is a flood of glucose molecules in the blood, the tendency is for that glucose molecules to become polymerized and therefore stored in the form that can be mobilized for future use. So that's exactly what happens. The liver, the liver synthesizes glucose, rather synthesizes glycogen, the storage form of glucose, from glucose that's found in the blood immediately after a carbohydrate-rich meal. Right? Muscles can also do that. Can also synthesize glycogen. Right? Now, before we consider the synthesis of glycogen, let us consider the glycogenolysis first, or the degradation of glycogen. The degradation of glycogen naturally entails the decomposition of glycogen into glucose. And what activities, what you can think of that might entail the degradation of glycogen? Well, what do you think? Starvation. Say, for example, if you're not eating anything at all, or if you're fasting, then your body will have no choice but to metabolize the glycogen stores that you have. In fact, it is the glycogen stores that are first metabolized um, when you are fasting. Then afterwards, your body will then turn on your fats, and ultimately, when you run out of fats, it will turn on your own proteins or amino acids. Um, we're going to study that in the future. But not only in the cases of fasting or starvation does one metabolize um, glycogen, but also during exercise, like during intense and strenuous exercise, the body um, tends to utilize glycogen, especially the muscles. Remember, we discussed before the anaerobic glycolysis, and you said that during conditions of anoxia, in other words, when you're doing a very strenuous exercise, that you're very intense and strenuous exercise, but there's no time for oxygen to be delivered into your muscles. So your muscles will have no other choice but to um, to utilize glucose using anaerobic glycolysis because there's no oxygen present to ultimately oxidize pyruvate into the and encourage it to go to the tricarboxylic acid cycle and oxidize the reducing equivalents that are formed therein. So what happens is that, as we're going to learn in the future, the tricarboxylic acid cycle is shut down, and so your muscle does not have any choice but to metabolize glucose anaerobically through glycolysis. The problem with that is that the yield of glycolysis, remember, is not in ATP is not that high. It's just two ATP molecules for every glucose molecule that is metabolized. And so during strenuous exercise or during intense exercise, your muscle will have to what in order to sustain muscular activity to provide enough ATP for your contracting muscles. The muscle will have no choice but to eat up a lot of glucose. And where does this glucose come from? This glucose comes from the breakdown of glycogen stores in your muscles, right? In your muscles, right? Ultimately, um, this glycogen is lysed into not to glucose, but to a metabolite of glucose that we're going to learn in a moment. And this metabolite of glucose, specifically glucose 1 phosphatase, enters the glycolytic pathway anaerobically, where it leads to the accumulation of lactic acid, which causes like cramps or muscular pain you feel during the process of anaerobic or when you're doing such strenuous exercise. Alright? Okay, now let us turn our attention to the process of glycogenolysis. Alright, now glycogenolysis is the breakdown of glycogen into its components. As mentioned, glycogen consists of glucose, but naturally you're not going to end up with glucose in glycogenolysis. Instead, you're going to end up with glucose 1 phosphate, right? And we're going to look at the mechanism of that lysis or glycogenolysis um, um, pathway in a moment. So let me use my pointer. Alright. Glycogen is cleaved by phosphate to give alpha D glucose 1 phosphate. As you can see here, this is glycogen. And glycogen, imagine that it's a polymeric glucose, a highly branched polymeric glucose consisting of alpha 1 4 glycosidic linkages as well as alpha 1 6 glycosidic linkage. The process is not hydrolysis, it is phosphorylysis, because you're using a phosphate ion in order to cleave glucose, or rather in order to release glucose 1-phosphate from the molecule. So this phosphate ion attacks the glycogen in the process, releasing glucose N-1. In other words, it's glycogen that is one less glucose molecule, and you have glucose 1-phosphate as the as the product of your reaction. You release glucose 1-phosphate. Now, cleavage reaction, as I mentioned, is phosphorylysis and not hydrolysis, because you're using a phosphate ion instead of water in cleaving the molecule into its component. No ATP is involved in this reaction, and the reaction is catalyzed by the enzyme called glycogen phosphorylase. Later, we're going to consider more study. We're going to have more to say about the properties of the enzyme glycogen phosphorylase. Right? Okay. So this is the first step in the process of glycogenolysis, the release of glucose 1-phosphate. Right? But remember, what happens is that you're releasing, again, during that strenuous activity or intense muscular activity, when you're doing a strenuous exercise, your muscles tend to undergo anaerobic respiration, and they need a lot of glucose molecules. This is a lot of glucose molecules as a source of energy. Now, this is not a glucose, right? This is glucose 1-phosphate. Remember, that's going to be metabolized in glycolysis. And how does that enter, or how does this metabolite enter the process of glycolysis? Remember, the process of glycolysis, the first step is actually the phosphorylation of glucose into glucose 6-phosphate, right? This is not glucose 6-phosphate. So what's going to happen is that in order for this metabolite to be, or the substance to be metabolized in glycolysis, it will have to be converted or isomerized to glucose 6-phosphate. And that's exactly what happens. The second reaction, the glucose 1-phosphate, is isomerized to glucose 6-phosphate by the enzyme phosphogluconeotase. Glucose 1-phosphate is converted into glucose 6-phosphate. Right? And then this glucose 6-phosphate can then enter the glycolytic pathway, the process providing the muscle with glucose. And you will have to remember, the muscle is lysing, or is decomposing its glycogen at a very significant rate, so that in order for the muscle to have enough glucose to sustain its strenuous activity. In other words, you're providing the muscle with a lot of glucose molecules in the form of glucose 1-phosphate. Now, I want you to notice that this reaction does not entail the consumption of ATP, because remember, in usual normal glycolysis, glucose is converted into glucose 6-phosphate via what? Coupled reaction with ATP, or adenosine triphosphate. So in this case, you're bypassing that reaction in the energy investment phase, so that in fact the the what do you call that, the yield, quote unquote, for glucose molecule, the ATP yield for glucose molecules, quote unquote, ATP yield, quote unquote, for glucose molecules in glycolysis that comes from the glycogenolysis of glycogen is actually 3, right? Um, uh, Actually, 3. I mean, how, how many how many ATP molecules do you generate? Okay. In the case of just normal glucose from the bloodstream that is metabolized in glycolysis, it will need 2 molecules of ATP. Remember, for the investment phase, and then 4 molecules of ATP are going to be formed in the payoff phase. So that's going to be a net of 2 molecules of ATP. In this case, you're not um, using up, you're not effectively um, using two molecules of ATP in the energy investment phase. Or just because this is already glucose 6 phosphate, right? So what effectively is that you're bypassing the first phosphorylation step in glycolysis. So you just needed one ATP in the energy investment phase, and then you generated four ATPs in the energy payoff phase. So the net yield is 4 minus 1. So three ATP molecules for every one potent glucose molecule that comes from glycogenolysis, right? Okay, so but the structure of glycogen is actually a branched molecule, right? It's a branched molecule, so you can think of it as this molecule that has a number of different branches. So the question is, how do you take care of, or how do you hydrolyze the entire molecule if there are so many branches in it? So what happens is that, as you can see here, these are the 1,4 glycosidic linkages. This is the 1,6 alpha 1,6 glycosidic linkage. So as usual, or as we expected, the molecules of glucose 1-phosphate are released from this non-reducing ends, right? From this non-reducing ends, and you're going to reach a point in which the phosphorylase, the glycogen phosphorylase, will stop um, removing the molecules of glucose from this end, and that's going to happen when you have one, two, three, four molecules in this branch. In that case, what happens is that a debranching enzyme um, completes a breakdown of glycogen by first removing the branches. So what's going to happen is that it's a debranching enzyme. That debranching enzyme will transfer, say for example, this three. So when you end up with just four in one branch, the debranching enzyme will transfer one, two, three. There's three residues from there to here. So it's going to cleave that alpha 1,4 glycosidic linkage and transfer it here. So this will be available for further action of glycogen phosphorylase. And what's going to happen here? This is going to be um, um, hydrolyzed by the same debranching enzyme, but this is not going to yield glucose 1-phosphate. Remember, that's hydrolysis, so that's simply going to yield the molecule of glucose, right? Okay. All right. So the this transferred branch will continue to be degraded depending upon the need of the muscle cell. For example, if the muscle cell needs more glucose, and that will continue to be metabolized, right? So what we've seen, or what we just discussed, is the degradation of glycogen into its component glucose 1-phosphate as well as glucose molecule. And that again requires the participation of three enzymes. The first enzyme, if you'll remember, is glycogen phosphorylase. The second is phospho glucomutase. This one catalyzes the conversion of glucose 1-phosphate to glucose 6-phosphate. And the third is actually the debranching enzyme, right, which transfers this three residues into that other molecule. That end of the molecule in order to limit to trim down the branches, and then this molecule this then will then continue to be acted upon by the glycogen phosphorylase. This one with this branch will be hydrolyzed by the branching enzyme itself. Right, so you have three enzymes participating in this reaction, which ultimately yields the majority of which, of course, will be glycogen, rather, will be glucose 1-phosphate. And there's some very small fraction of it, which will be um, glucose, just a molecule of glucose. Alright, so now how about glycogen? Because I mentioned a while ago, after a meal, when you have a lot of when you have had a carbohydrate-rich meal, which typically do have, like you eat a lot of rice, there's a lot of glucose in the blood, and in the resting state, the organism will of course will have an excess or a lot of glucose, and the organism, or we for example, our system will therefore find ways to store this glucose in a form that can be metabolized further in the future in time of need. And that is exactly in the form of glycogen. Like, how do you synthesize glycogen from glucose? So, what happens is, first and foremost, it's not the exact reversal of glycogen breakdown to glucose, and that is important in metabolic processes. The the opposite processes are not occurring in reverse in exactly in exact reverse. There are steps in these processes that are pathways that are not encountered in the opposite pathway. We're going to learn more about that later. For now, let's turn our attention to the synthesis of glycogen from glucose. So the glycogen synthesis requires energy, alright, and this energy is supplied by the hydrolysis of uridine triphosphate. This is the structure of uridine triphosphate. It's similar to the structure of adenosine triphosphate. The only difference, instead of having adenine, you have uracil, right? So what happens here is that glucose has to be converted in a form that is activated. You have to activate glucose in order for it to be incorporated into your glycogen stores. Okay, so again, after a meal, you have a lot of glucose in the blood, and your body's not going to waste that glucose. And remember, if you have too much glucose in the blood, that is bad because that leads to diabetes, right? So your liver is going to absorb much of the glucose, the hepatocytes, the liver cells, going to absorb much of the glucose from the blood, and in the process convert it to glycogen. So the first thing that happens is that it is um, it is, I'm not, okay, so here, glucose is converted into glucose 6 phosphate. Of course, it's phosphorylated into glucose 6 phosphate. Afterwards, it's isomerized to glucose 1 phosphate, right? And that glucose 1 phosphate reacts with the uridine triphosphate to make UDPG. I'm not sure. Okay, so here is uridine diphosphate glucose. So this is uridine, and you have diphosphate glucose. So that's the activated form. The pyrophosphate is also formed, and um, um, it is actually the hydrolysis of the pyrophosphate into two inorganic phosphates that drive the formation of uridine diphosphate. Okay, so the UDPG is then added to a growing chain of glycogen catalyzed by glycogen synthase. All right. Um, so here's what happens. So this is your glycogen, right? And your like, of course, this is a simplified depiction of glycogen because glycogen has a lot of branches. So this carbon number 4 is this hydroxyl group at carbon number 1, 2, 3, 4 will then react with your UDP glucose. But what actually happens is that this carbon oxygen bond breaks in the process producing an oxonium ion, and this oxonium ion intermediate is then attacked by the hydroxyl at carbon number 4 in the process producing that glycosidic linkage, alpha 1 4 glycosidic linkage. Right, so we have a glycogen with has N residues, now it has N plus 1 residues. Okay, now um, this is happening not just at one end of a branch. Remember, this is happening at many ends, many non-reducing ends of many branches, and therefore, remember, the many ends, the ends of the many branches, the non-reducing ends of the many branches of glycogen molecule. So you're imagining you can imagine the molecule of glycogen then grows and polymerizes into into that polymer of very quickly because there are a number of points at which the molecule of glucose can be added, and therefore the molecule can be lengthened. Okay, the same can be said about and I forgot to mention that the um, uh, hydrolysis, or rather the phosphorylasis of glycogen. Because remember, as I said a while ago, a lot of glucose can be decomposed or can be obtained from glycogen. And that is exactly because the molecules of glucose are being lost not just at one end of the molecule, but at the many at the ends, the non-reducing ends of the many branches of the molecule glycogen. All right. Okay. So um, uh, so we've seen um, reaction, the degradation of glycogen into um, uh, into glucose 1 phosphate and the synthesis of glycogen from glucose 1 phosphate. Now we ask ourselves a question: how do you control the metabolism of glycogen? Because glycogenolysis is the breakdown of glycogen, while glycogen synthesis, or glycogenesis as we call that, is the synthesis of glycogen from glucose 1-phosphate. So these are two exactly opposite pathways, two exactly opposite processes. Notice that their end results are exactly opposite, but end results are exactly opposite, but the um, um, the processes, the steps in the processes are not exactly the same, right? They are not exactly the same. They are catalyzed in this case by two different enzymes. That's your one, okay? And the steps are not exactly the opposite of each other. One requires the presence of one requires phosphorylasis reaction, while um, um, the other one requires activation using uridine diphosphate. Now, there's something that I forgot to mention. When these molecules are lengthened, right, when these molecules are lengthened by addition of more and more glucose molecules, you will have to remember that the molecule of glycogen is a branched polymer. And so there's again not a debranching enzyme, but a branching enzyme. That branching enzyme will transfer certain portions of the growing chain and transfer it to say for example this part will be removed and will be cleaved and transferred into this carbon atom in order to create more and more branches, right? And that's how the highly branched molecule of glycogen is synthesized in the body. Okay, now going back to our previous question, how do you control the metabolism of glycogen? Right. First and foremost, the glycogenolysis and the glycogenesis cannot happen at the same time. Why? Because you're going to end up with futile cycles. You cannot you cannot metabolize glycogen at the same time synthesize it. That is wasteful. That will waste energy, the resources and the energies of the cell, not to mention precious time. So glycogen phosphorylase, which is involved naturally in the degradation of glycogen into glucose 1-phosphate, is a major control point in the synthesis and breakdown of glycogen. So glycogen phosphorylase activity can be allosterically controlled as well as controlled through covalent modification. First and foremost, let's look at this. Okay, now glycogen phosphorylase exists in two forms, the phosphorylase A and phosphorylase B. Notice that phosphorylase A is phosphorylated, while phosphorylase B is not phosphorylated. Another thing is that both of these two phosphorylases, or rather glycogen phosphorylase forms, like phosphorylase A and phosphorylase B, Both of them exist in the T form and in the R form. The T form is the inactive form, while the R form is the active form. All right. Now, let us first consider what happens. Say, for example, in the liver, um, in the liver, look at this diagram and see what happens. In the liver, glucose is an allosteric inhibitor of phosphorylase A. Okay, so see here. I'm not sure if you can see that, but hopefully you can. Um, the um, the um, the Did you notice the size of the arrows here? This is a what do you call that? A wider arrow, and this is a slimmer arrow. The direction of the arrows, or what do you call that? The width of the arrow indicates which form is actually favored. For example, in phosphorylase B, notice that the arrow directed, but is pointing in the direction of the T form is actually wider. That is because the equilibrium here favors the P form, in other words, the inactive form, right? While in the case of the phosphorylase A, it's the R form that is more favored, right? The R form that is more favored, all right? Okay, so the phosphorylation of of glycogen phosphorylase is one way of controlling its activity, right? One way of controlling its activity. And why do we say that is the case? That's the case because, excuse me, once, excuse me, the T form, remember, or rather the phosphorylase B exists in the R form and the T form. But the T form is the favored form of phosphorylase B, and the T form is inactive, right? So phosphorylation of phosphorylase B into phosphorylase A via phosphorylase kinase. Remember, kinases are enzymes that phosphorylate, right, using ATP as a phosphate source. So the phosphorylase kinase phosphorylates the phosphorylase B into phosphorylase A. Okay, we now have phosphorylase A. But notice that the equilibrium or disequilibrium favors the R form of phosphorylase A, and the R form is the active form. So you can therefore you therefore see that phosphorylation here is a strategy of the cell to activate the glycogen phosphorylase, right? Activate glycogen phosphorylase. Um, the phosphoprotein phosphatase does the opposite. When the kinases phosphorylates, the phosphoprotein phosphatase removes the phosphate group. And what are phosphorylated here, by the way, are the serine residues. This is a diamidic enzyme. Okay, so let's go back to what happens in the liver. Okay, so this is the liver, for example, or in the liver, glucose is an allosteric allosteric um, inhibitor of phosphorylase A. What happens is that what? Look at that. The glucose um, inhibits the activity of phosphorylase A in the process, causing it to be what happens? The the glucose inhibits the activity of phosphorylase A, and it what? It encourages the conversion of the R form, the active form of phosphorylase A, to the T form, the inactive form of the phosphorylase A. And this is happening in the liver. So does this make sense? Does this make sense? So okay, so when do you think the liver will have glucose or a lot of glucose? When you just had a meal, right? When you just had a meal. When you just had a meal, then your liver will have, or the hepatocytes will have a flood of glucose coming from the blood, and so the glucose there will inhibit the activity of glycogen phosphorylase. Does that make sense? Yes, it makes sense because there's already a lot of glucose, and therefore there is no need for your liver to what? To hydrolyze its or to what do you call that? To release more glucose 1 phosphate from glycogen. In other words, there's no need for the liver cells or for the hepatocytes to release glucose if there's already a lot of glucose in the blood. By the way, the primary function of the liver is to one of the primary functions of the liver is the maintenance of blood glucose level, and it maintains blood glucose level through glycogenolysis as well as gluconeogenesis. We're going to study gluconeogenesis later. For now, I want you to focus on glycogenolysis. Okay, again, there's already too much glucose after a meal, and so there's no need for the liver to release its glucose from glycogen. And that's exactly why the activity of the glycogen phosphorylase A is inhibited by glucose. It makes sense. When there's a lot of glucose, there's no need for glycogen phosphorylase A activity. In other words, there's no need to release glucose from glycogen. And we're going to notice in this case, not only is the phosphorylase A inhibited by glucose by converting it into the inactive form of phosphorylase A, notice that the conversion to the T form, and remember, only the T form is dephosphorylated, right? Only the D form is acted upon by the phosphoprotein phosphatase. It's not the R form. So the conversion of phosphorylase A into the T form um, encourages the dephosphorylation of phosphorylase A by phosphoprotein phosphatase into phosphorylase B. And remember that phosphorylase B primarily exists in the T form, the inactive form. Again, consistent with the fact that there's no need for active glycogen phosphorylase when there's a lot of glucose in the blood, or that happens when immediately after a meal, right? Okay, but what happens if um, uh, it's not? What happens if it's not the case? Say for example, in the muscle. So okay, let's consider what happens in the muscle. In the muscle, what do you have in your muscle? Your muscles, for example, are doing strenuous exercise. Not only that, your muscle is utilizing a lot of, uh, of ATP, right? Because it's doing this strenuous exercise or intense exercise or whatever muscular activity. In that case, what's going to happen? What's going to happen? Okay, you can think of a muscle cell as being in a charged state, or in an when you say charged state, it means it has a lot of energy. Say a lot of energy, then you have a lot of ATP and you have a lot of glucose, and therefore glucose 6 phosphate, and and an energy deficient state where you have very low ATP. And when you have very low ATP, by the way, you have a lot of AMP. Low ATP is equivalent to high AMP, or adenosine monophosphate. Say, for example, you have this muscle that is doing a lot of strenuous exercise, and so um, uh, the muscle therefore has used up a lot of its ATP already, and therefore will have a lot of AMP in it. AMP is an allosteric activator of the T form of phosphorylase B, converting it into the active form. Does that make sense? Yes, it makes sense because your muscle is performing the strenuous activity, and this muscle has consumed a lot of ATP, and therefore that's why you have a lot of AMP, or adenosine monophosphate. Since it has already consumed a lot of ATP, then it needs to generate more energy. And where will that come from? Again, it will come from glycolysis, right? And if that comes from glycolysis, then you will need a lot of glucose, and that glucose will come from glycogenolysis of the glycogen in the muscle. That is why you need an active phosphorylase, and that active phosphorylase is obtained upon allostatic activation of the inactive phosphorylase B into active phosphorylase B by the binding of adenosine monophosphate. All right. Okay. Now, let us consider the case when there's a lot of ATP. When there's a lot of ATP, um, what's going to happen? When your cell already has a lot of ATP, then it does not need to generate more ATP because there's already a lot of ATP. That means that you don't need glycolysis, you don't need Krebs cycle or citric acid cycle. You don't need the electron transport chain at that moment to generate a lot of ATP through oxidative phosphorylation. In that case, what do you think? Do you need glucose to metabolize? No, you do not need glucose to metabolize, right? And so, if you do not need glucose to metabolize, then that means that you do not have need for glycogenolysis. The glycogen has to stay glycogen. There's no need to metabolize glycogen into glucose. And that's exactly what's happening here. Because adenosine triphosphate, which corresponds to a charged state of the cell, um, the adenosine triphosphate will bind to the active form of phosphorylase B and converting it into an inactive form. Again, that makes sense because you do not have need for any glucose, and therefore you do not need to to release glucose from a glycogen, right? Also, glucose 6-phosphate is also an allostatic inhibitor of phosphorylase B. When you have a lot of glucose 6-phosphate, that means that it's either, for example, when you have a lot of glucose 6-phosphate in your muscle, it means that you just had a meal, right? Okay, you just had a meal, and therefore you're you have a lot of glucose, and you have a lot of glucose 6-phosphate, and there's no need for your glycogen in the muscle to be metabolized into glucose 1-phosphate and converted into glucose 6-phosphate because you have already a lot of glucose 6-phosphate from the blood that you can use for synthesizing ATP, and so better yet for just the glycogen to stay glycogen for future use. And that's exactly what's happening here. When you have a lot of glucose, you have a lot of glucose 6-phosphate, the glucose 6-phosphate acts as an allostatic inhibitor of phosphorylase, converting it into the T form, the inactive form. All right. I'm hoping that that explanation has been clear and that you're able to grasp how we control, or how the allosteric as well as covalent modification strategies for regulation of glycogen metabolism is accomplished by systems, living systems, by organisms such as ourselves, right? Okay, now the activity of we've talked about the activity of the glycogen phosphorylase. The activity of glycogen synthase is subject to the same type of covalent modification as glycogen phosphorylase. However, the response is opposite, which again makes sense. You cannot activate the glycogenolysis and activate glycogen synthesis at the same time. That will be very wasteful. So whatever regulatory mechanism active in this case, glycogen synthase and glycogenolysis, um, whatever regulatory mechanism that activates the degradation of glycogen must deactivate the synthesis of glycogen and vice versa. Alright? Okay. So hormonal signals like glucagon or epinephrine stimulate the phosphorylation of glycogen synthase. After phosphorylation, glycogen synthase becomes inactive. At the same time, the hormonal signal is activating the phosphorylase. Okay, so um, um, what happens, say, for example, when I think you might have encountered this, the fight or flight syndrome, right? You're either going to fight with superhuman strength or you're going to flee with superhuman speed. But when, say, for example, I believe you've encountered, maybe you have heard stories of people who are able to carry very heavy loads when during um, emergencies. For example, there have been reports of people being able to carry refrigerators out of a burning house. And what else? You're able, for example, you're cornered by a bully or somebody that's trying to bully you, and you found it in yourself that you're either going to flee with superhuman speed, but you're going to run as fast as you can so that he will not catch you, and you manage to actually do that. Or you're going to fight for your life and fight with superhuman strength, and you discover that you're able to do that. Right? This has a basis actually because epinephrine, that's the hormone responsible for that. Epinephrine, as we mentioned here, stimulate the phosphorylation of glycogen synthase. So after phosphorylation, glycogen synthase becomes inactive, but the same hormone, epinephrine, activates glycogen phosphorylase. And what you remember, glycogen phosphorylase releases glucose, right? Increases glucose available um, uh, in your muscle and in the blood, if you're talking about the liver. So what happens is that you are provided with an energy source, glucose, and if you're doing and if you're talking about the muscle will do what will metabolize that very quickly in the process of glycolysis, allowing you to get as much ATP as you can, and that explains why you're able to accomplish this superhuman feats under emergencies or in emergencies, right? But of course, afterwards, when you get after you did that, you realize or you feel tired, and like the moment after you did, it, you feel tired. Why? Because of the accumulation again of lactic acid and some of our intermediates. Okay, so but the point here that I'm trying to make is that the glycogen synthase and the glycogen phosphorylase are regulated such that when one is activated, the other one is deactivated. All right. Okay. All right. So glycogen, in summary, is a storage form of glucose in animals, including humans. Glycogen releases glucose when energy demands are high. Glucose polymerizes to form glycogen when the organism has no immediate need for the energy derived from glucose breakdown, and this happens when you just had your meal. Glycogen metabolism is subject to several different control mechanisms, including covalent modification like phosphorylation and allosteric effects like the effect of glucose and adenosine triphosphate, adenosine monophosphate, and glucose 6-phosphate. Right? Okay. Now, We've just discussed glycogenolysis. Now we turn our attention to the process called gluconeogenesis. Gluconeogenesis is actually the opposite pathway of the opposite of glycolysis. Whereas glycolysis metabolizes glucose into pyruvate, gluconeogenesis synthesizes glucose from pyruvate. All right, and you're going to ask yourself, that's why it's called gluconeogenesis, the synthesis of new glucose. We're going to ask ourselves the question, when and why is this happening? Why is this happening? Right? Okay, this is very important. The one of the, as I mentioned a while ago, not a while ago, as I mentioned some time ago, the one of the important function of the liver is the maintenance of blood glucose level. After some time, for example, when you're fasting, first thing that gets uh, consumed, of course, are your glycogen stores. All right. Afterwards, fats are metabolized. But afterwards, what happens? You ran out of your glycogen stores already, and you ran out of fats. How do you supply the needs of your body? Um, your body will need to generate its own glucose, right? And this glucose molecules are going to be synthesized from pyruvate. There are a number of different sources of pyruvate. Pyruvate can come from what? From the lactic acid that you generate during anaerobic respiration or anaerobic glycolysis. But um, pyruvate can also come from amino acids, the metabolism of amino acids. That's why what's going to happen is that when you're fasting, you're not only getting thinner, you're actually not just thin in the sense that you're losing fat. You're actually getting thin, right? You're metabolizing them. Your proteins. Proteins are metabolized into amino acids, and the carbon framework, the side chains of the amino acids are then metabolized. And one of the many intermediates involved there, many possible end products of the metabolism of amino acids are pyruvate and oxaloacetate. Pyruvate and oxaloacetate, these are important intermediates that are ultimately used in the synthesis of glucose. And this glucose are once they are synthesized, are transferred to the blood, so to maintain blood glucose level, and ultimately transferred to um, the muscles or whichever, especially the brain cells, which need ATP or glucose as energy source. Okay, so gluconeogenesis is not the exact reversal of glycolysis. That is, pyruvate to glucose does not occur by reversing the steps of glucose to pyruvate. And why is that the case? Remember that the process of glycolysis, in fact, all metabolic processes are exergonic overall. So the opposite of it will be endergonic and will therefore be non-spontaneous. So you cannot reverse a pathway and expect it to happen spontaneously. So you will have to, if you want to reverse a pathway in the sense that you want to have a net effect that is opposite that first pathway, then you can appropriate some of the steps that are part of that pathway, but you have to bypass some of the other steps, especially the committed steps and the regulatory steps in uh, in glycolysis in this case when you're talking about gluconeogenesis. Remember that there are three irreversible steps in glycolysis: the conversion of phosphoenol pyruvate, the conversion of fructose 6-phosphate to fructose 1,6 bisphosphate, and the phosphorylation of glucose to glucose 6-phosphate. These are three regulatory steps in glycolysis, and what? These are the three steps that are bypassed in gluconeogenesis. Okay? The net result of gluconeogenesis is reversal of these three steps, but by different reactions and using different enzymes. Exactly what happens? The first step in gluconeogenesis is the conversion of pyruvate to oxaloacetate, and that happens by way of this reaction. pyruvate reacts with ATP and carbon dioxide in the presence of pyruvate carboxylase in the coenzyme biotin process producing oxaloacetate. Alright. Now, this enzyme is actually subject, pyruvate carboxylase is subject to allosteric control. It is activated by the enzyme acetyl-CoA. Alright. Now, we haven't yet discussed acetyl-CoA, but acetyl-CoA is actually the product of pyruvate dehydrogenase. Pyruvate dehydrogenase oxidizes pyruvate into acetyl-CoA, and that acetyl-CoA is the one that enters the Krebs cycle, or the tricarboxylic acid cycle. Now, at this point, what I need you to know is that when you have a lot of acetyl-CoA, that means that you have a lot of pyruvate, which means that you have a lot of uh, of glucose, right? We have a lot of pyruvate carboxylase, then a lot of acetyl CoA, and that means that you have a lot of of a lot of glucose, in the sense that acetyl CoA comes from pyruvate, which in turn comes from the oxidation of glucose. Okay. Alright, so pyruvate is then converted into oxaloacetate. The next step is a decarboxylation. By the way, this reaction happens in the mitochondria. So this reaction happens in the mitochondria. Okay, the next is a decarboxylation of oxaloacetate, okay, which is coupled with a phosphorylation by GDP to give phosphoenol pyruvate. Okay, phosphoenol pyruvate carboxykinase catalyzes the phosphorylation of oxaloacetate, or rather the decarboxylation of oxaloacetate and its eventual phosphorylation into phosphoenol pyruvate. Okay, the net reaction is carboxylation, of the carboxylation, decarboxylation is pyruvate being converted into phosphoenol pyruvate. Remember, the phosphoenol pyruvate is the one that where is it? Phosphoenol pyruvate is the one which is ultimately converted into glucose. Now, here's the mechanism of the pyruvate carboxylase reaction. The reaction um, requires the presence of carbon dioxide because it's carboxylated, remember, and it's carboxylated to oxaloacetate. Um, First, the carbon dioxide is converted into carbonic acid. Carbonic acid is activated into becoming this is an anhydride, carbonic phosphoric anhydride, and that then reacts with biotin, right? Carboxylating the biotin, which when it reacts with the um, this is the enolate of pyruvate, all right? Enolate of pyruvate in the process produce oxaloacetate. All right. Now the oxaloacetate then undergoes reaction with GTP catalyzed by phosphoenol pyruvate carboxykinase into phosphoenol pyruvate. Right. The phosphoenol pyruvate is um, uh, then utilized in the synthesis of glucose. All right. Okay. Um, where am I? The the other steps in gluconeogenesis are the reverse of glycolysis, except of course for the three reactions that I've already mentioned. The other different reactions in gluconeogenesis relative to glycolysis is shown here. Remember fructose 1,6-bisphosphate. From fructose 6-phosphate to fructose 1,6-bisphosphate in glycolysis, that's catalyzed by phosphofructokinase, right? In this case, a different enzyme catalyzes the conversion of fructose 1,6-bisphosphate to fructose 6-phosphate, and that's fructose 1,6-bisphosphatase. Alright, Now, the fructose 1,6-bisphosphatase is an allosteric enzyme that is inhibited by AMP and activated by ATP. Does this make sense? The fact that it is inhibited by AMP and it is activated by ATP. First, it is activated by ATP. It makes sense, right? If you already have a lot of ATP, then you do not need to metabolize or to oxidize glucose, right? You do not need to um, uh, you already have a lot of ATP, so the fructose 1,6-bisphosphatase, the enzyme that converts fructose 1,6-bisphosphate to fructose 6-phosphate, is activated. Like you don't need ATP anymore, and so you're what? You're not you're encouraging gluconeogenesis. You're encouraging gluconeogenesis in the liver because this this glucose molecules will then ultimately be stored in the form of, uh, of glycogen, or will ultimately be this fructose 6 phosphate will ultimately be converted into glucose. Now, why is it inhibited by AMP? Why do you think it is inhibited by AMP? When you have a lot of adenosine monophosphate, what did we say? That is a state where the cell is deficient or does not have energy, right? It does not have energy. And so this makes sense in the sense that fructose 1,6-bisphosphate has to be channeled into glycolysis and therefore for the production of ATP, right? Because your cell is lacking in ATP when you have a lot of adenosine monophosphate. All right. Now, another reaction is the hydrolysis of glucose 6-phosphate to glucose and inorganic phosphate. Right. So this glucose 6-phosphate and then glucose. This is accomplished by glucose 6-phosphatase. All right. So those are the three enzymes that are, or those are three reactions that are not, but are different from the um, uh, reactions in glycolysis. The other reactions are just the same. Okay, now we have learned, I haven't mentioned this before, but there is another allosteric, a mode of allosteric control that's exerted on glycolysis and gluconeogenesis. And this is primarily done by or through the molecule fructose 2,6-bisphosphate. Now, the fructose 2,6-bisphosphate is an allosteric activator of phosphofructokinase. In other words, when there's a lot of fructose 2,6-bisphosphate, phosphofructokinase 1 is activated, which means that glycolysis is activated. Because remember, the reaction catalyzed by phosphofructokinase 1 is the committed step in glycolysis. And therefore, um, uh, um, uh, the presence of fructose 2,6-bisphosphate, it activates phosphofructokinase 1, and therefore glycolysis is favored. Fructose 2,6-bisphosphate is an allosteric inhibitor of fructose bisphosphate phosphatase. Okay, now what does that mean? This makes sense, right? Because remember, fructose 2,6-bisphosphate activates phosphofructokinase 1, the enzyme that produces fructose 1,6-bisphosphate from fructose 6-phosphate, and therefore that fructose 1,6-bisphosphate is needed for the generation of ATP, the process of glycolysis. Now, or even in oxidative phosphorylation. Now, does it make sense that the same fructose 2,6-bisphosphate deactivates fructose bisphosphate phosphatase? Yes, because what? As I mentioned, the, the, the organism cannot favor both opposing processes at the same time. If it favors glycolysis, then it must not favor gluconeogenesis. Otherwise, you're wasting time and energy, right? And also the fact that you have a lot of fructose 2,6 bisphosphate suggests that your cell is in need of ATP, and therefore that's why it's encouraging phosphofructokinase in order for you to generate more ATP in glycolysis and ultimately more ATP in the Krebs cycle and in the and through oxidative phosphorylation. In other words, the cell is desperate for ATP. Um, uh, if you and that's why it makes sense for fructose 2,6 bisphosphate to inhibit the synthesis of glucose or to inhibit gluconeogenesis because you are in an energy deficient state. You're not in a position to generate glucose. You're actually desperate for glucose. You actually need glucose. Okay. Okay. High concentration of fructose 2,6 bisphosphate stimulates glycolysis, while a low concentration stimulates gluconeogenesis. Again, it makes sense because if you have low concentration of fructose 2,6 bisphosphate, that means that your cell does not need ATP, and therefore there's no need for you to metabolize glucose. And if there's no need for you to metabolize glucose, um, then that means that what you have enough energy and you will have to this time the liver synthesizing um, uh, glucose for not for itself, by the way, synthesizing glucose so that it can replenish the glucose, for example, in the blood or in some of our um, uh, tissues. Okay. Um, all right. Now, the concentration of fructose 2,6 bisphosphate in a cell depends on the balance between its synthesis, which is catalyzed by phosphofructokinase 2, and its breakdown, which is catalyzed by fructose bisphosphatase. Okay. Now, each enzyme is controlled by phosphorylation and dephosphorylation. So, let's look at this. Okay. Um, this is the fructose 2, where phosphofructokinase 2. Phosphofructokinase 2, remember, synthesizes fructose 2,6 bisphosphate from fructose 6 phosphate. And um, fructose 2,6 bisphosphatase, on the contrary, decomposes, or not decomposes, but hydrolyzes fructose 2,6 bisphosphate into fructose 6 phosphate. Alright? Um, uh, Now, what do you? I give you a moment to consider this diagram and analyze or look at it and see what do you think is happening. Okay. Now, this plus sign, this green plus sign, indicates phosphorylation. All right, and look at that. When you, by the way, what was this is the enzyme phosphofructokinase 2 and fructose 2,6 bisphosphatase. They're actually found in one and the same molecule. Right? Or the activity is actually found in one and the same molecule. Okay, so the protein kinase phosphorylates fat. All right, so you see as P. Plus means it is phosphorylated in a phosphorylated state, while um, uh, minus means dephosphorylated. So notice that the phosphorylation actually favors the activity of fructose 2,6 bisphosphatase. All right, of fructose 2,6 bisphosphatase, while the Dephosphorylation favors the activity of phosphofructokinase 2. Okay, now let me look at that. And I wanted to look here. Fructose 2,6 bisphosphate, what does it do? It activates phosphofructokinase 1, as we have discussed a while ago. It encourages, therefore, glycolysis, while fructose 2,6 bisphosphate inhibits fructose 1,6 bisphosphatase, which means that it inhibits the process of gluconeogenesis, right? Okay. Now, these are the different mechanisms of metabolic control um, of of mecha of metabolic control. Actually, no, this is not the one that I'm talking about. Where is it? This is the reactions of glycolysis and their standard free energy changes. It's just shown here via values of the delta G for the process of the process that's involved in glycolysis. I'm not sure why there's the table for the mechanism of metabolic control where it went, but that table essentially just tells you that metabolism is controlled via phosphorylation. It's also controlled by allosteric regulation, where small metabolites bind to the enzyme and activates and deactivates it. And the phosphorylation, as I mentioned, phosphorylation is important in the sense that hormones, as we've seen in the case of epinephrine, and later we're going to learn about insulin and glucagon. Um, these hormones actually affect their or cause their effect to be felt via phosphorylation, cascade of processes that ultimately cause phosphorylation or dephosphorylation of the enzymes involved in the metabolic pathway, specifically glycogenolysis or um, glycogen synthesis or glycogenesis. Okay, all right. Um, Now, this substrate cycling is another strategy for controlling metabolic pathway aside from allosteric regulation, aside from covalent modification through phosphorylation, dephosphorylation. Opposing or substrate cycling refers to the phenomenon where opposing reactions are catalyzed by different enzymes, and each opposing enzyme or set of enzymes can be regulated independently. And we've seen that. We've seen that in the case of the formation of fructose 1,6 bisphosphate and its hydrolysis, right? The enzyme that catalyzes the conversion of fructose 6 phosphate to fructose 1,6 bisphosphate is phosphofructokinase. The opposite reaction is not catalyzed by phosphofructokinase. It's catalyzed by fructose 1,6 bisphosphatase, right? And that is important because when you have two different enzymes that's acting upon or that catalyzes two opposing reactions, then you can regulate them independently. Because if it's just one enzyme that catalyzes the forward and the reverse reaction, then you encounter a problem. Because once that enzyme is regulated or is allosterically activated or deactivated, the forward and the backward reactions will be activated at the same time or deactivated at the same time. That's why it's important that two different enzymes catalyze this opposing steps, because the same metabolite can have an activating effect on one enzyme and a deactivating effect on the other. Okay? This is the reaction that I was talking about. Fructose 6 phosphate becoming fructose 1,6 bisphosphate and fructose 1,6 bisphosphate um, uh, um, uh, becoming converted into fructose 6 phosphate with inorganic phosphate. This reaction is just the opposite of the above reaction, if you notice. If one enzyme catalyzes this reaction, then we have a problem, as I mentioned a while ago, because because both the forward and the backward reactions are going to be catalyzed. All right. Okay. Now, we've mentioned before the accumulation of lactate in muscles, right, during a strenuous exercise. It causes cramps or an uncomfortable feeling. So, what happens? What happens to the lactate? The lactate, as I mentioned before, is actually transported to the liver through the bloodstream, right, through the blood. And this lactate is ultimately oxidized back into pyruvate. And um, that pyruvate, what happens to that pyruvate then? That pyruvate is then used by the liver to synthesize glucose in the process of gluconeogenesis. So nothing is wasted. Under vigorous and that process actually, conversion of lactate, um, the conversion, the transport of lactate from the muscles to the liver and from the eventual conversion of lactate in the liver back into pyruvate is actually called the Cori cycle in honor of the discoverers. Under vigorous anaerobic exercise, remember glycolysis in muscle tissue converts glucose to pyruvate. NAD plus is regenerated by reduction of pyruvate to lactate. In other words, pyruvate acts as an oxidizing agent. Now, the lactate in the muscle is transported to the liver, where it is reoxidized to pyruvate and converted to glucose. Now, what happens to that glucose? That glucose um, uh, is then transported back to the muscle and used as a source of energy. So notice that the liver shares the stress of the vigorous exercise, right? This is what happens. Remember, so you have your muscle, for example, there is muscle, and what's happening in the muscle is glycolysis. You're doing a strenuous exercise, glucose converted to pyruvate, but the pyruvate oxidizes NADH in order to regenerate NAD plus, which is necessary for continuous anaerobic oxidation, anaerobic glycolysis. Now, the lactate that builds up is transported through the bloodstream to the liver. The lactate is oxidized to pyruvate, where you have lactate oxidized by NAD plus becoming converted to pyruvate, and then this pyruvate is um, used in the synthesis of glucose through the gluconeogenesis, and that glucose is then transported back to the muscle. All right. Notice in the muscle there is low NAD plus to NADH ratio. That is why it was necessary for NADH to reduce pyruvate in order to regenerate NAD plus. In the liver there is a lot of NAD plus, and that's why it's able to oxidize lactate to pyruvate, right? So I hope that Cori cycle is understood. Okay. Now, there is the enzyme pyruvate kinase. I'm not sure if you remember what that enzyme is. Pyruvate kinase is what? If you remember, pyruvate kinase. Where have you encountered the enzyme pyruvate kinase? It's in the last step of glycolysis, right? It's where you convert phosphoenol pyruvate to pyruvate. That's the enzyme that catalyzes that. All right. So let's look at the control of liver pyruvate kinase by phosphorylation. All right. Excuse me. So we have low blood glucose levels. So first and foremost, this is the phosphorylated pyruvate kinase, and it is less active compared to the dephosphorylated pyruvate kinase, which is more active. Okay, now let us see what happens. So when you have low blood glucose level, what happens? Or let's look first when you have a high blood glucose level. When you have high blood glucose level, the what happens? The um, uh, the pyruvate kinase is phosphorylated, right? When you have low blood glucose level, the pyruvate kinase is phosphorylated into a less active form. Now, does that make sense? You have low blood glucose level. Always ask yourselves if such makes sense. So if you have low blood glucose level, so what do you think is necessary here? Do you think you need to remember the liver? This is the liver what you're talking about, whose primary function is the maintenance of blood glucose level. So if there's low blood glucose level, the uh, the uh, the um, uh, pyruvate kinase is phosphorylated and is converted into a less active form. Does that make sense? Yes, because you do not want glycolysis to happen in your liver when there's a need for the synthesis of glucose, right? Because there's low blood glucose level, and so the liver has to synthesize glucose in order to increase the amount of glucose in the blood, and therefore it has to encourage gluconeogenesis. That is why low blood glucose level converts the pyruvate kinase from the active to the inactive form in order for it to not consume glucose in the process of glycolysis, but to generate but to in the process um, encourage the synthesis of glucose. Now, when you have low blood glucose, um, okay, so what happens when let's see, if you have a dephosphorylated pyruvate kinase, it's look at let us first look at the low blood glucose level again. Low blood glucose level, this inhibits the conversion into the more active form, right? The low blood glucose level inhibits the conversion of the pyruvate kinase, the less active form, to the dephosphorylated form. Again, does that make sense? Yes, because you have low blood glucose level, and therefore the liver should not um, uh, engage in glycolysis. It should synthesize um, uh, glucose. All right. Okay. That is why the dephosphorylated pyruvate kinase um, uh, form is not favored when you have low blood glucose level. Okay. Now, the dephosphorylated pyruvate kinase is the active form, right? So this converts phosphorylated pyruvate again to pyruvate. Look at that. What molecules activate the pyruvate kinase? ATP and alanine. Does it make sense that, I'm sorry, it inhibits because that's negative, right? So does it make sense that adenosine triphosphate is an allosteric inhibitor of pyruvate kinase? Yes, you already have a lot of ATP and therefore there's no more need for glycolysis to proceed because you already have a lot of ATP. And so this last step in glycolysis is inhibited. Now I'm not sure if you noticed that, but alanine, I'm not sure if you're familiar with that, but alanine is actually the alpha keto, rather the amino acid form of pyruvate, because pyruvate is the alpha keto acid of alanine. Now we're going to learn more about the alpha keto acid and amino acid and amino acid metabolism. But for now, it is important to note that pyruvate is actually converted into alanine. All right. When you have a lot of alanine, that means you have a lot of pyruvate, and therefore there's no more need to synthesize pyruvate. That is why alanine inhibits this pyruvate kinase, because when you have a lot of alanine, again, that means you already have a lot of pyruvate, right? Now, fructose 1,6-bisphosphate encourages the activity, or rather activates pyruvate kinase. Does that make sense? Remember, fructose 1,6-bisphosphate is the product of phosphofructokinase 1, right? When you have a lot of fructose 1,6-bisphosphate, that means you have just um, uh, you have a buildup of glucose. There's a lot of glucose that's being funneled into glycolysis, and therefore that fructose 1,6-bisphosphate has to be metabolized through glycolysis, and that's why it's activating this step, the last step in glycolysis, right? Okay. Now, here are the major control points in carbohydrate metabolism. First, the last steps in glycolysis are major control points in the glucose metabolism. The hexokinase, the reaction that's catalyzed with phosphorylates glucose into glucose 6-phosphate. Hexokinase is inhibited by high levels of glucose 6-phosphate. Again, does that make sense? Yes. When you already have a lot of glucose 6-phosphate in the cell, then that means you have a lot of energy source already, and that there's no need for you to take in more glucose. When glycolysis is inhibited through phosphofructokinase, glucose 6-phosphate builds up, shutting down hexokinase. Again, as I mentioned, when glycolysis is inhibited through phosphofructokinase, all right, um, uh, there's already a lot of glucose 6-phosphate. It builds up, and so there's no point in getting in more glucose from the bloodstream, because you already have a lot of glucose 6-phosphate. There's already buildup of glucose 6-phosphate in the first place. Pyruvate kinase is an allosteric enzyme. Um, uh, it is inhibited by ATP and alanine, as I've already mentioned. It's activated by fructose 1,6-bisphosphate. Pyruvate kinase isocymes have three different subunits. The M predominates in the muscle, L in the liver, and A in our tissues. These liver isocymes are subject to covalent modification. Okay, now, in summary, there is a number of control mechanisms that operate in carbohydrate metabolism, and this include allosteric effects, covalent modification, substrate cycles, and genetic control. In the mechanism of substrate cycling, the synthesis and the breakdown of a given compound are catalyzed by two different enzymes. Alright? Okay. Alright. Um, uh, Now, here we turn to the last part of our discussion for this chapter. It's called the pentose phosphate pathway, or it's also called the hexose monophosphate shunt pathway. And this is an important pathway because it provides the NADPH, the reducing equivalence that is necessary for biosynthesis, and it also acts as a source of ribose, which is important, of course, important components of ATP, adenosine triphosphate, and the nucleotides, which are important for what process of replication, and therefore its process of cell division. The pentose phosphate pathway (PPP) is an alternative to glycolysis and differs in several important ways. In glycolysis, ATP production is important. In the pentose phosphate pathway, this is not the case. As the name implies, there are 5 carbon sugars, including ribose, are produced from glucose, and that, as I mentioned a while ago, the NADPH, an important biosynthetic reducing agent, um, um, is generated from this reaction. All right, it begins with two oxidation steps that generate NADPH, ultimately giving ribulose 5-phosphate, and following the series of trans-ketylation and trans-aldolation reaction, which effectively simply shuffles the carbon atoms or the carbon fragments from one sugar to another, the process producing 3, 4, 5, 6, and 7 carbon monosaccharide phosphates. So here is what is happening. I hope that you can see that because it's quite small. So these are the first step, glucose 6-phosphate. Remember, glucose 6-phosphate is also an intermediate that's found in glycolysis. Remember, glucose is phosphorylated by hexokinase to glucose 6-phosphate. In this case, the glucose 6-phosphate is not metabolized or is not isomerized to fructose 6-phosphate. It is um, um, oxidized into 6-phosphogluconate in the process, reducing NADP plus. Remember, this is not NAD plus, but this is NADP plus, reducing NADP plus to NADPH. Alright, the process, this is 6-phosphogluconate, and the 6-phosphogluconate is then further oxidized by another enzyme to produce ribulose 5-phosphate, and again producing another equivalent of NADPH. So two molecules of NADPH have been generated in this case, and this is very important because these NADPHs are important for what? For the processes that are um, implicated in the synthesis of of molecules like lipids, like amino acids, like proteins, and so on and so forth. All right. Now, notice that the ribulose 5-phosphate that's produced here, this is the oxidative portion of the pentose phosphate pathway. Now, this is the reshuffling of the sugars. The ribulose 5-phosphate that you produce there is now found here. It is isomerized to ribose 5-phosphate. It is also isomerized to cellulose 5-phosphate. Notice that this ribose 5-phosphate is important for nucleic acid biosynthesis, like as I mentioned, important in the process of cell division because that is where you encounter replication. And it's also important because nucleotides are important, like we got ATP, right? ATP is a nucleotide, so for that, and even GTP. Okay. Um, uh, so what happens next is reduction between ribose 5-phosphate and cellulose 5-phosphate, producing cedoheptulose 7-phosphate. It's a 7-carbon sugar and a 3-carbon sugar, glyceraldehyde 3-phosphate. Now, these two further react with each other to produce erythrose 4-phosphate and fructose 6-phosphate. Alright? Alright. Now, this erythrose 4-phosphate reacts with another molecule of cellulose 5-phosphate to in the process produce fructose 6-phosphate and glyceraldehyde 3-phosphate. Now, I want you to notice that these two are intermediates of glycolysis, and I want you to notice as well that these steps, transketolation, is the transfer of 2 carbon fragments, while the transfer of 3 carbon fragments is called transaldolation. So transketolation, transaldolation reactions. This essentially this reshuffling of carbon fragments from one sugar to another. The interconversion of sugar phosphates here is reversible. Okay, it is reversible, and therefore, depending on the need of the cell, um, uh, the this reductive this oxidative pathway um, can be favored, or this pathway can be favored. Okay. As I've mentioned, the carbon shuffling reaction are catalyzed by transketolase and transaldolases. Now, the control of the pentose phosphate pathway is maintained by glucose 6-phosphate. The glucose 6-phosphate dehydrogenase. I'm not sure if okay here. This enzyme is catalyzed by glucose 6-phosphate dehydrogenase. So the control of the pentose phosphate pathway is maintained by glucose 6-phosphate that can be channeled into either glycolysis or the pentose phosphate pathway. In other words, you control this step, right? Because this step can, as mentioned here, can be channeled into either glycolysis or the pentose phosphate pathway. Okay, G6P channeling into glycolysis. If ATP is needed, this will not go into pentose phosphate pathway, but will go into glycolysis. If NADPH or ribose 5-phosphate are needed, then we're going to channel glucose 6-phosphate to the pentose phosphate pathway. All right. Now I'm not sure if you're familiar with that, but there is a newborn screening. Okay, before I jump into that, I want you to know that um, it is important, or antioxidants are important in the cells because they fight radicals that tend to cause disruption of cell components and decomposition of cell components. So the only reducing agent that is available to a red blood cell, since it does not have any mitochondrion, is the NADPH. It's the NADPH. So this NADPH, for example, prevents damage to the hemoglobin. It prevents damage to the uh, the to the cell components that are caused by oxidizing agents or free radicals. It does that through an indirect pathway. Glutathione, and I believe you've encountered glutathione before. Glutathione, it is a peptide that acts as a reducing agent. It makes sure that the integrity of hemoglobin and that the integrity of the components of the red blood cell um, are preserved even in the presence of oxidizing agents. Okay, but this glutathione, in accomplishing that task, is actually oxidized, and what converts back oxidized glutathione into glutathione is NADPH. It reduces that back into glutathione. Okay, the problem is then when you have red blood cells that have deficiencies in glucose 6-phosphate dehydrogenase, because if you have deficiencies in glucose 6-phosphate dehydrogenase, then you won't be able to produce NADPH. Much more, you won't be able to proceed to the next step, which produces another NADPH. So that means that your cell will have no defense against free radicals, and therefore your red blood cells will be subject to wholesale destruction. It will just simply fall apart and be destroyed as a result of the presence of oxidizing agents like radicals and so on and so forth. This ultimately leads to hemolytic anemia, right? And this is a serious disease. That's why newborn screening or the screening of newborns usually have this as one of the tests is the glucose 6-phosphate dehydrogenase activity, right? Okay, that's what I wanted to say. What else? So the this is where what I'm looking for. Apparently, this has been transferred into this portion. I'm going to go back to this later. I want to look at the pentose phosphate pathway and glycolysis. Remember, where is the glucose 6-phosphate? Glucose 6-phosphate. Here, the glucose 6-phosphate is common to both the pentose phosphate pathway in blue and the glucose 6-phosphate, rather the glycolysis in pink. Now, the glucose 6-phosphate will be channeled to glycolysis if there is a need for ATP. But if what you need are reducing equivalents like NADPH and ribose 5-phosphate, typically this happens when the cell is undergoing cell division, right? Because you need a lot of nucleotides in that case, and you also need reducing equivalents in that case. So if you need NADPH and ribose 5-phosphate, and then the glucose 6-phosphate is channeled to the pentose phosphate pathway. That is why it's an alternative to glycolysis, because instead of going to glycolysis, it goes to pentose phosphate pathway in that case. Now, if notice that if you need If you do not need NADPH, you just need ribose 5-phosphate, you can actually accomplish that from the intermediates of glycolysis, like glyceraldehyde 3-phosphate and fructose 6-phosphate. Through transbutylation and transaldylation reaction, you can produce ribose 5-phosphate for that, right? If you just need ribose 5-phosphate and you do not have intense need for NADPH, okay? In that case, only the non-oxidative part of the pentose phosphate pathway is um, is encouraged, not the oxidative um, part of the pentose phosphate pathway. Now, here is a summary that I want to talk about. Ultimately, we've learned of the carbohydrate metabolism and the different pathways for carbohydrate metabolism, and of course the metabolic control. Metabolic control is affected through allosteric effect or allosteric control, and it is through effectors or substrates, products, or coenzymes of a pathway that inhibit or activate an enzyme, like in the case of phosphofructokinase. This responds rapidly to external stimuli, like to allosteric molecules, or allosteric activators or allosteric inhibitors. Covalent modification, this refers to the inhibition or activation of enzyme depends on the formation or breaking of a bond, like phosphorylation, right? This also responds rapidly to external stimuli. An example would be glycogen phosphorylase and glycogen synthase. Substrate cycles, this is the mode of control when you have two opposing reactions such as formation and breakdown of a given substance are catalyzed by different enzymes, like in the case of phosphofructokinase 1 and fructose 1,6 bisphosphatase in the case of glycolysis and gluconeogenesis. They also respond rapidly to external stimuli. And lastly, the genetic control. The amount of enzyme present is increased by protein synthesis. This is long-term control than the other mechanisms that are listed here. Um, we've encountered one of these example, like induction of the beta galactosidase and the lack of peron, right? Now, hopefully you have learned a lot in our discussion, and that you've learned a lot about carbohydrate metabolism and the control of carbohydrate metabolism. In the next discussion, we're going to consider the process called Krebs cycle. Like what happens to pyruvate under aerobic conditions when there's energy, or rather when there's oxygen available for the system. Remember, glycolysis, yes, is useful, but the yield in ATP for that process is quite small. Alright, just 2 ATP for one glucose molecule. That is quite small. So the organisms take advantage of the presence of oxygen and use oxygen to, in the process, completely oxidize glucose into carbon dioxide, which allows for the harnessing or the extraction of greater amount of energy and more ATP molecules. Just how much more we're going to learn later when we study Krebs cycle and the oxidative phosphorylation. Right? Okay.